Uh, the presentation today is structured in two parts. I will go over the first part where we'll talk about OptiStruct solutions for nonlinear analysis, and we'll also discuss why OptiStruct proves to be a viable alternative for nonlinear analysis. After that, I will hand over controls to Ujjwal, who will walk us through a couple of workflows that are enabled with HyperMesh and SimLab, where we discuss the setup for some of these nonlinear analysis problems inside of OptiStruct. So to get started, I would like to discuss a couple of some three important factors or three key factors when evaluating a solver. So the first one is functionality. We want to ensure that the solver provides the basic functionality that we need for our analysis needs. The second key factor is benefits. So beyond providing just the functionality, what are the benefits that we get to the process by looking at a particular solver or an alternative solver? And the third key factor is value. So what is the value add to the organization that we get by moving to a particular solver? Now, these are also the three reasons why one should look at an alternative solver for nonlinear analysis, such as OptiStruct. So I'd like to discuss these three factors in the context of OptiStruct during the course of the next half hour or so. So we start off with the functionality aspect. So for those who may not be all that familiar with OptiStruct and its capabilities, what is OptiStruct? OptiStruct is a proven and comprehensive structural analysis solver. Over the past 25 years or so, we have evolved from a basic linear static solver into a fully featured comprehensive solver with solutions across nonlinear analysis, vibrations and acoustics, integrated fatigue analysis, and even multi-physics. Optimization continues to be a differentiator for us, and we continue to invest and develop new and innovative optimization technology that in turn can be used to generate these innovative, lightweight, and structurally efficient designs. OptiStruct is based on modern solver architecture, and what I mean by that is when we're implementing certain features and functionality into OptiStruct, we're keeping in mind how these features can be scalable. We recognize that model sizes are increasing, as is complexity, and we want to make sure that the solutions can be scalable on a high number of cores or high number of nodes, and also keeping in mind the workflows. We want to ensure that the workflows are streamlined so that we have a much better process when running the analysis or the optimization. So here's a look at some of the features of OptiStruct at a very high level. So we're talking about a bird's eye view, and it also shows you how OptiStruct has evolved as a solver. And some of the functionality that we're most popularly known for were first developed over 20 years ago. So technologies such as topology optimization and linear statics were developed more than 20 years ago. But since then, we've continued to increase our development, and about 10 to 15 years ago, we focused more on the NV8 side of things. And then more recently, about the last 5 to 10 years or so, we added functionality for nonlinear analysis, fatigue analysis, and so on. So you see how the OptiStruct solution has evolved into a fully featured and comprehensive finite element solver. Now, if I were to look at these different analysis types or these different features and put them into various different solutions, here's what that would look like. So today with OptiStruct, we have specialized solvers and solutions for stiffness, stability, and strength, which would include linear and nonlinear analysis. It would include static analysis as well as transient. We also have dedicated and efficient solvers for vibrations and acoustics. We have a comprehensive set of features for both analysis as well as on the diagnostic side that allow us to run vibrations and acoustics analysis and optimization. On the fatigue side, we have an integrated fatigue solver, which also includes capabilities for weld fatigue as well as vibration fatigue. When it comes to studying materials and manufacturability, we have solutions that allow you to study advanced materials such as composite materials, as well as alternative manufacturing techniques such as 3D printing. And we do also have various types of solutions available for multi-physics analysis. And I'll talk briefly about some of those solutions in the upcoming slides. Optimization continues to be a key philosophy at Altair. And so when we're looking at implementing any analysis feature, the next logical step from there is how do we enable that for optimization? because if we're analyzing a particular response, if we're measuring a particular function, the next step is how do we improve that function, and that's where optimization comes in the picture. Now, all of this is built on a foundation that facilitates large-scale computing and parallelization that allows us to take advantage of the latest developments in both hardware as well as software. So for the scope of today's presentation, I want to focus on three aspects of the OptiStruct solutions. The first one is on stiffness, stability, and strength. We'll also look at some capabilities on the multi-physics side, and then focus on the large-scale computing. But to start with, let's look at some of the capabilities for stiffness, strength, and stability. And I want to focus just on the nonlinear analysis capabilities. Now, we know that when it comes to nonlinear analysis, there are three basic elements to nonlinear analysis, and that includes the effects of nonlinear contact, nonlinear material, and nonlinear geometry. So if you look at the solutions that are supported for nonlinear contact, so here's a look at what we support. When it comes to contact discretization, there are different types of discretization methods. So we have nodes to surface, surface to surface, as well as self-contact. And you can see that depicted through this animation on the far right-hand side, where you see this tube that's collapsing on itself. We also have various types of contact interfaces. So you have the tie contact and the freeze type of contact. You can also use sliding with friction. And the contact can also be used in a thermal analysis, in which case it behaves as a thermal contact. Now, based on the type of problem that you're solving, you can choose to use either small sliding or large sliding contact. So, for example, if you look at this head and block assembly on the screen, that's an example of where we would use a small sliding formulation. And then the two animations on the lower left and in the middle showcase applications where we would use large sliding type of contact. Now, all the contact formulation can be included in the optimization. So on this slide, I have three different examples. The first one is of a brake caliper housing, and you can see this model includes the various components of the brake assembly, including the pads and so on. We're also including various contacts with friction, and the idea here is to run a topology optimization to identify the optimal design for the housing while considering the effects of friction in the design as well. The result that you see in the middle is that of a free shape optimization, which is also a non-parametric shape optimization. And the idea here is we're trying to optimize various sections of this connecting rod in order to control the stresses while minimally affecting the mass. And the connecting rod example is a nonlinear model where we have 3D bolt pretension. We also have an interference fit at the bearing region and various types of load conditions, such as the firing load and bearing loads that we're trying to optimize the design against. And finally, on the right-hand side, the third application is a large shape change optimization, where with every design iteration, we update the contact pairs. And in this case, the example is to identify what is the optimal placement of this rib structure within that channel so as to meet certain performance requirements. And that could be maybe stiffness requirements, it could be for frequency or stresses and so on. So as you can see, the contact can be included in any optimization formulation. The next general nonlinearity is nonlinear materials. And in OptiStruct, we support multiple types of nonlinear material models. So we have the very commonly used elastoplastic material model. And this supports small strain as well as large strain plasticity. We also have a range of different hyperelastic material models. So from the most simpler representation of the near hook material model to the more detailed representation of the Aruda Boyce or Ogden material models can all be represented in OptiStruct. We do also support gasket materials. So for those of you who run powertrain type of analysis, you can define the gasket materials, which is typically represented through a series of loading and unloading curves. And those curves can also be temperature dependent. Additionally, if you did have your own material model, you could build that constitutive material model and then use that through a user-defined function inside of OptiStruct. So you can see over here, if it's on Windows, we use dynamic libraries or shared libraries on Linux to basically integrate this user subroutine and have OptiStruct use that particular material model. It's the same mechanism that we use to integrate OptiStruct with multi-scale designer. So multi-scale designer is a microscale solver. And the idea over here is you want to carry out an accurate assessment of the material behavior, which is typically addressed at the constituent level. So for example, if you look at it on the right-hand side, we have a composite placed with a hole. We want to model it at the part scale, so we're modeling it at the plate scale. But in order to calculate the material behavior accurately, we need to simulate the effects of the material down at the constituent level. So the results that you see on the screen are basically the material behavior occurring at the fiber and the matrix level. We also keep looking at ways by which we can improve the efficiency of processes. In this case, this is one such approach where we are trying to improve the efficiency in the context of optimization when it comes to evaluating for plasticity. So what we're using here is based on the Neuberg correction, and the idea here is to very quickly and efficiently evaluate plasticity from a linear analysis. Now, I can always look at the detailed plasticity results from a full-blown nonlinear analysis, which is also going to be fairly expensive. But over here, if I want to run multiple iterations, if I want to run an optimization, I can very easily do this using the Neuberg correction, optimize my design, and then at the end do a final detailed validation using a single nonlinear analysis. So that in that way, it's a much more efficient process and helps cut down the time while accounting for plasticity or permanent set type of responses. So that brings us to the third element of nonlinear analysis, which is nonlinear geometry. And essentially, most of what we discussed in terms of contacts and materials apply to both small and large displacement formulations. Additionally, on the large displacement side, we also support hyperelasticity. We also support joints and as well as transient analysis. And you can see that depicted through the animation on the lower right hand of your screen, where we showcase a low-speed bumper impact problem using a nonlinear transient type of analysis. So apart from this, there are various other types of nonlinear analysis functionalities available with OptiStruct. Of course, we don't have the luxury of time to go through every single feature that's available, but I did want to show you a representative set of features that are available with OptiStruct today. So for example, you can do bolt pretension analysis. You can also do a preloaded analysis. And in the case of a preloaded analysis, you could use a nonlinear analysis. It could be a small displacement or a large displacement formulation problem, and use that as a preload condition to run your vibration study. We also have a lot of results output and write out a lot of diagnostic information. This is very useful to study the convergence behavior of a part or of your analysis. Or maybe, let's say, the analysis has some difficulty in converging. You may want to understand what's going on with the analysis and look at certain diagnostic information. And we write out a lot of very useful information to be able to do that. More recently, we also added capabilities for axisymmetric analysis, including contacts. As mentioned previously, we do support joint elements, as well as certain specialty types of analysis, like bow distortion, which is used for powertrain type of analysis. In addition to this, as mentioned, there's a lot of other features. So we do support things like creep. We support materials such as viscoelasticity, viscoplasticity, as well as cohesive elements. So very comprehensive set of solutions when it comes to nonlinear analysis. The next topic I want to briefly touch upon is multiphysics, and I want to focus on two applications over here. The first one is multiphysics that's enabled through coupling of AccuSolve and OptiStruct, and this is to solve problems for fluid structure interaction or even thermal fluid structure interaction. So we have AccuSolve, which is our CFD solver, and it basically solves the fluid domain problem. And the fluid domain will exert certain loads on the structural domain, which in turn will deform, and that deformed structure will change the flow field around it. So in order to accurately capture this bidirectional coupling, we have this multiphysics solution between AccuSolve and OptiStruct. So the example that you see on the lower left-hand side is an oil and gas application where we're studying the effects of wave motion on this riser structure. Now on the right-hand side, it's a coupling between Flux and OptiStruct. This is to predict electric motor noise. So flux is a low-frequency electromagnetic solver from where we can calculate the electromagnetic forces. We then use those electromagnetic forces and run a vibration study inside of OptiStruct. And then we can take it one step further, where we can do an acoustic simulation and then study the sound pressure levels or the far field noise levels. So moving to the third topic, which is large-scale computing and parallelization. So I do want to mention that most of the analysis types that we support, including optimization, is supported for domain decomposition. And what that means is you can take a large model and you can split it and run it on multiple number of nodes and multiple number of cores to get a much faster turnaround time in your analysis or your optimization. And so on the right-hand side, we have two examples. The one on the top is of a typical nonlinear analysis type of problem. And you can see over here, we've scaled up to 196 cores and across multiple nodes to achieve that level of scalability. And on the lower part of your screen, lower right-hand side, it's where we've used domain decomposition with the global search option to increase the scalability in running the global search option to try and find a more global optimum solution. So let's look at a couple of different applications of how we've used some of the technology that's available in OptiStruct to solve real-world industry applications. So in part 2 of today's presentation, Ujjwal will be focusing on some automotive applications. So for the two examples that I will be discussing, I'll talk about one example in the aerospace industry and another example from the oil and gas industry. So this first example from the aerospace industry is that of a flex coupling. And the flex coupling essentially behaves like a U-joint. So on the right-hand side, you have the yellow shaft, which is like the driver shaft. And on the left-hand side, you have the green shaft, which is the driven shaft. Now, the driver shaft can have some loads that are acting on it, which may cause misalignment. And the idea of the flex coupling is that it should isolate that motion so that the misalignment is not transferred over to the driven shaft. Now, this type of model is typically run with large displacement. It includes contact with friction between the various components. There's also bolt pretension, and then we apply the loading on the assembly. So we have torque on the shaft, and then we define and enforce displacement to simulate the misalignment load cases. So here's a look at the displacement from the three chain subcases. And what I mean by the chain subcases means that subcase 2 follows subcase 1, and similarly subcase 3 follows subcase 2. And you can see the effects of the pretension and then the torque loading and then the subsequent enforced displacement on the entire assembly. And correspondingly, we can look at the stresses again for each of these subcases based on the sequential loading. This next example is that of an oil and gas example. So this is a well-bore flange analysis. And these are structures that are used in exploring for oil and gas, for example. Now, if you look at the structure, at the center, we have this pink component, which is essentially a gasket material. And the idea over here is to create a seal between the upper flange and the lower flange. Now, once this is inserted into the earth, the gases basically flow through this section on the inner surface. And so we basically have to ensure that when the pretension load is applied and the various other operating loads are applied to the model, that the seal is maintained and that there is no chance of leakage. Again, this problem over here is a large displacement problem. We consider elastoplastic material behavior of the seal. It includes contact with friction, there's bolt load, and then we have the two operating load conditions. So the internal pressure to represent the fluid pressure on the inner surface, and then we have the external tension that applies on the top surface of the upper flange. And the background to that particular load case is that maybe at the surface there could be an operator that might relocate or might move the structure, and that will create an upward tension causing the two flanges to separate. And the idea is to see that under all those load conditions that there is no breach in the seal. So again, we run this as a chained analysis, and you can see the first subcase was the pretension where the two flanges were closed down due to the bolt pretension. And in the second subcase, you can see that there is a slight separation between the two components. and that's due to the fluid pressure that acts on the inner surface of this particular structure. Now, the third subcase is the external tension, where we pull up on the upper component, and you can see that it forces a much greater separation between the two parts. Now, once the analysis is run, we want to look at the stresses, see if everything is in order, either in the flanges or in the bolt regions. And then we also want to look at the seal behavior. So on the left-hand side, we are looking at plastic strain, and you can see over here that at certain regions in the seal, the plastic strains are a little under 20%. And on the right-hand side, we're looking at contact traction or contact pressure. And based on the design, there are certain recommendations that identify minimum sealing pressure. And if we monitor the contact pressure at a point where the contact pressure drops below the sealing pressure, that would indicate a potential for a breach in the seal and then cause a leakage in the assembly. So with that, you'll see that OptiStruct offers a very comprehensive set of solutions for nonlinear analysis. And the next key factor to consider is the benefits. So we have various functionality that's available, but what are the benefits that we have to the process? And I want to talk about two particular benefits over here. The first one is the single model multi-attribute workflow. Before we talk about the single model workflow, let's look at a typical workflow that we have today. So let's say there's a part or an assembly that I'm trying to analyze. We have to analyze this particular structure for multiple different load cases. And typically what's involved is building separate models based on the type of loading. So for example, I build one model for vibrations, I could build a separate nonlinear model, and potentially even a third model to run my fatigue analysis. Now, when you look at this type of environment, it requires multiple models to be built. We use different solvers as well as different formats. Now, if you don't build multiple models, you need to convert the model from one solver format to the other solver format. So it's a very time-consuming task as well as error-prone task. The other major concern over here is model version management. So if there's a design change that's made, it's imperative that that design change is captured by all the models that you build. Otherwise, you would have a certain group in an organization that might be working on an outdated model. And now, in this situation, if you throw in optimization, it's going to add to increased complexity because you're potentially talking about a separate tool to create the parameterization and possibly even yet another tool to actually run the optimization study. So it's not a very efficient environment to do these types of analysis. Now, if you look at this in contrast to the workflow with OptiStruct, it's a much more streamlined workflow with OptiStruct because now we just build one model and all this loading, the load cases that we want to consider are simply identified as different subcases. So for example, over here, subcase 1 could be a vibration subcase, subcase 2 could be a nonlinear subcase, subcase 3 could be fatigue, and then I can loop optimization around all these subcases and run it in a single model. So I don't spend time on doing the model conversions. I minimize the chances of errors due to those conversions. And when you look at model version management, again, it's not a concern because any change to the design is made to that single model, and it's automatically updated in that model itself. And the best part is if you're looking at using these models for optimization, these models are optimization ready. And what I mean by that is if you're looking at running these models with HyperStudy, the models can be directly used with HyperStudy, or even if you're looking at using the multi-model optimization framework in OptiStruct, these models can be used directly in that environment. So what is the benefit with using a single model workflow? So here we've mapped the process for a typical vehicle subassembly type of model build process. And we're studying the time spent in building a mesh and the model setup for analysis. So you can see over here, if you look at the typical process that we see in the industry today, we build a single model. In this case, the first model that we build, we spend a certain amount of time. We build it for dynamic stiffness. We then assume that we're using the same model, and we add additional input to that model to create the model that I need to run my strength analysis. And then I use the strength analysis, run some additional, or perform some additional operations to build my durability model. And by the end of it, I've ended up spending about 15 man-hours to set up these different load cases on the multiple models. Now, when it comes to using OptiStruct, since I'm building just a single model, I can define all these load cases on that single model. In addition, I can go a step further and loop the optimization around this entire study. So now the time spent in this whole process is down to 9 hours. So the difference that we're looking at over here is very significant. We're talking about a 40% improvement in the overall process, and that's for a single design iteration. And we know that typically any development process involves multiple design iterations and even multiple variants. So if you look at the process benefits overall, they tend to stack up very quickly. So here's an example of the single model workflow where we looked at this subframe design, and we need to analyze and optimize it for dynamic stiffness, strength, as well as seam weld fatigue. Now, typically these are run as using separate solvers. Also, there's different groups that run these models. They also work on different models. Now, with the single model workflow, I can build just a single model and run all these just as separate subcases inside of OptiStruct. So we do a baseline check of the design, and you can see based on certain targets, the design failed for dynamic stiffness and strength, but it passed for durability. So how do we improve the design? We then choose to wrap an optimization around it. So in this case, we ran a gauge optimization. So we're optimizing the thickness of these different members. We're trying to minimize the mass of the design while having constraints on dynamic stiffness, Neuber strain, which is used to control the permanent set in my design. And we also have a constraint on the weld damage. And at the end of the optimization process, you can see by incorporating all these constraints in a single model, we have a design that meets all the requirements and in addition is about 3 kilograms lighter. So there's a lot to be gained using this single model workflow. The second major benefit is design optimization. And this is an area where we have continued to develop new and innovative functionality. So there's multiple different optimization disciplines that's available with OptiStruct. You can apply them at the concept level stage and at the fine-tuning stage. And the goal over here is to be able to apply optimization throughout the entire design process and improve the potential of coming up with a lightweight, structurally efficient type of design. Additionally, there is a range of different manufacturing constraints that can be applied. So, for example, if you're casting a component, if it's an extruded component, or even if it's a 3D printed component, there are certain manufacturing constraints that are available. You could also look at manufacturing constraints for advanced materials like composites. So, depending on the type of manufacturing method and the type of component that you are developing, you can use different types of manufacturing constraints to drive the optimization results. And the last point on the optimization benefits is that of the exhaustive response library. Now, why is this important? Because these responses are essentially design criteria. So, for example, we're talking about stresses, displacements. It could be frequencies, it could be fatigue life, it could be damage, and so on. So with OptiStruct, we have over 75 such responses that basically allow you to formulate the optimization problem to account for the different physics that you need to capture in your optimization. And so that's another key differentiator where this allows you a lot of flexibility in formulating the optimization problem to meet your specific requirements. So coming to the third core factor, and that's the value. So what is the value that's being provided to the organization by using OptiStruct? And in this case, I wanted to talk specifically about increasing the analysis throughput. And what I mean by increasing analysis throughput means we want to increase the number of concurrent solver jobs. We want to have more jobs that are running rather than spending time in the queue. And we have a couple of different disruptive licensing mechanisms that allow us to do that. So the first one is a per job licensing and license decay, where essentially it gets relatively cheaper the more number of cores you add, and it also gets relatively cheaper the more number of jobs you run, and thereby facilitating the running of DOEs or optimizations where we have a large number of runs that are going on. Additionally, we have another disruptive model that's based on a solver node licensing. And what this does is the licensing is based on the number of nodes that are in use and not based on the number of jobs that are being run. And this is becoming more important today as we look at modern the hardware architecture, where the nodes have a high core density. So now you can run multiple jobs on a single node, and the licensing is then based on the number of nodes used and not on the number of jobs. So just to kind of to summarize on our discussion today, we indicated that when we're looking at identifying an alternative solver, or in that process, we need to consider functionality. And we've seen that OptiStruct has comprehensive and accurate solutions, and they're also highly scalable solutions. But going beyond functionality, what are the benefits that we're going to add to the process? And the first one is that the solutions are enabled for optimization. So you can apply optimization throughout the design process to improve your chances of coming up with a structurally much more efficient and better design. But beyond that, there's also the improved workflows. So we talked about the single model multi-attribute workflow, where you have a significant benefit in your overall process time. And that time can now be spent more effectively in trying to improve the design rather than trying to convert data from one format to another format. And then going one step beyond that, what is the value that we get to the organization? So we spoke about the disruptive licensing model. So essentially, the more jobs you run, the more cores you use, the relatively cheaper that it gets. And all this is using HyperWorks units. So the same HyperWorks units that you use to run OptiStruct are the same HyperWorks units that you use to run HyperMesh, for example. And they're also the same HyperWorks units that can be used to run any third-party application as part of the Altair Partner Alliance. So that helps you in consolidating and lowering your software spend. And then we also want to look at the support aspect of things. And at Altair, we provide the leading support, proactive and timely support, and we want to ensure that you make best use and are successful in deploying the technology that we are providing. And I think this builds a very strong case for OptiStruct to be considered as an attractive alternative for a nonlinear analysis. So at this point, I would like to end part one of the session and transition controls back to Will.
Thank you, Warren. Our next presenter today will be Ujwal Patniak, and I've just passed the controls over to you, Ujwal.
Yes, Will, can you see the screen? You hear me clear?
I can, thank you.
Thank you. So continuing what Warren had showcased for the nonlinear solutions, let me go over the workflows. The workflows primarily we're talking about is the two great pre-processing tools Altair has, HyperMesh and SimLab. So first of all, I will probably walk you through a process with two examples in HyperMesh and SimLab, but let's look at a quick round of things with respect to these two pre-processing tools. HyperMesh is a general purpose pre-processing tool. SimLab is a CAD integrated, tightly integrated, live-sync, physics-based environment. HyperMesh is domain-driven, automotive, aero, and NVH. SimLab is a physics-driven. It's mostly talks to structures, fluids, and EMAG, electromagnetic flux, etc. HyperMesh desktop is more automation environment system enabled. You can do your automations. There are a lot of built-in systems there. SimLab is user-defined automation. So you run your simulations, you do your physics, and then you can save your automation. So let's see some of these things in the workflows, what I'm going to go through. So let me start with a door abuse use case. Let me go through that. We will see probably about 5 use cases. One of them is the normal mode analysis, that is dynamics, and then we do nonlinear analysis, global lateral, and palm print and dent, SAD and hit. The key features I will be touching base here is the nonlinear quasi-static analysis, nonlinear transient analysis, in the case where the door is open and door is closed. Some of the nonlinear features will be like rigid bodies, definitions, some FE joints while the door is moving around, and then nonlinear materials, large displacement, contacts, add, remove parts. So let me go through some of the processes in HyperMesh in the order. We'll go through a quick model browser, load step browser, contact browser, and a solver browser to quickly review and then submit the job and look at the results. So let me jump from here to HyperMesh. So if you have seen HyperMesh before, or if you didn't, in the HyperMesh environment, on the left side is the model browser, where you can see the list of entities which is already there for the existing model. This is the model which already has everything set up for the door use cases. I will review it one by one in terms of the order of steps. The first thing, the components. In the list of components, what we have in this particular model, you can see it has a composition of the shells, the solids, the joints, the bushes, lots of parts in this particular model. You can actually review them by clicking over and right-clicking and looking at the details of the part definitions and stuff. In this model, as you see, you have a indentation, which is like a dent, and also there is a palm print, and also then there is several other cases. So we have like a fine mesh and a coarse mesh parts, which are highlighted in this particular model. So they come in and then go off. So there is a mod change, which is like active and deactive stuff. In terms of definitions of materials, this is a great thing about nonlinear, the nonlinear materials, what we have. Here you can actually see in OptiStruct, in HyperMesh environment, is more transparent to the user in terms of the solver text step. So you can see a math card defining the linear step, and then it goes into the plastic definitions using the math S1 card. User has an option to feed in the table of nonlinear stress versus strain curve, which is what is fed in here, and so on. The material definitions are all here by create, and then you can start picking the type of material you want to go into, all the great nonlinear materials which Warren spoke. And then in terms of properties, the property definitions are linked from the material. As you see, if I start looking at any of these properties here, they already have assigned materials, and then you start defining thicknesses, the properties of beams, stiffness of bushes, etc. So that gives you a comprehensive step-by from a part definition to you moving into a material and property. Now, for this particular model, for this particular use case, we have contacts. Okay. Now, this is something troublesome in terms of processes unknown. Here in HyperMesh, you have an auto contact definitions where the user can go and pick all the set of components, what he wants, and then he can say, okay, this is the search distance I'm giving you, and this is the standard settings I'm giving you. Go create and find contact for me. Later, the user has a table ability to go and edit these on the fly. So once I go pick them and I define the type of contacts, what is needed for that particular part, I also have contact definitions based on property, that is friction, and also the large sliding contact or infinite sliding contacts, what we have in OptiStruct. So once I do an auto find search of these contacts and I get them and I trim the surfaces and so on, I can always go and edit them at any point of time, and also I can also review these contacts at any point of time. So beautifully on the screen on the live, as I move on from contacts from top to bottom, you can actually see the contacts moving from the hinges to the doors and the panels. Now, that is the contact setup, one thing after defining your materials and properties. So fundamentally, we have come a long way in terms of model definitions for this door reviews. Now, the last thing, important stuff. Let's look at definitions of loads. You have a dent load, you have a palm print loading, you have the sag load, you have a normal mode. All these things are set up in the load step browser. So you can actually go and create a load step browser. Here, what I will do is I'll review these, one of these. So I can go and edit these options, and I can actually show you that this is a nonlinear static analysis. Great, this is a header, and then the load references. So this gives us a nice list of cards which are defined in this particular subcase. There is continual sub, which is continuation of anything. So there is no continuation because this is the first step. And then there is stabilization if there is any stabilization needed for your contacts. NLADAP is a nonlinear adaptation of the nonlinear convergence criteria and stuff. User defined, there are automated methods, but user has ability to go and edit them. And allowed gives you a lot of output options in terms of nonlinear analysis. So these highlighted stuff are what is already there, and these dotted ones are something hinting to the user that you need these to do nonlinear analysis. Mind you, if you don't have them, you're not going to set up any kind of load setup here. So once I pick these guys and I start clicking on summary of the table, it pretty much gives me a good summary of the list of analysis what I have. So it gives me a detail of what is my load, what is the analysis I'm going, what is the load references, what is the output I'm asking. So it gives me a good summary of the sets what I have here. Now, this gives me a complete setup of in terms of model definitions and loads and stuff. On the right side, I have a very neat way of looking at all the solver cards. So this gives me an options where I can read like a card deck, like reading the core solver text file or something, where it gives you the highlights of what are there in the input-output option, the subcase information, anything to do with the bulk definition. So this gives you all the information what is needed if you want to in case review them. This is one place to go and review the solver deck. Now, one other thing is before you once we have the model set up and everything, before you go and hit run, we can also have a model checker, which will come nicely integrated in OptiStruct in HyperMesh profile, where it gives you a quick check of the number of errors. This is based on the solver errors. HyperMesh computed all these information inside HyperMesh, so it can tell you these are goods and bads in the model and make sure you get some attention out of this. Finally, once you're done, you can right-click and click on OptiStruct, and you can just go and hit and solve. So that's as simple as it can get. So now if I just jump from here, assuming I submit the job, I can actually, in the HyperMesh desktop environment itself, I have a nice post-processing where I can just click on the hyperview side of it, and I can start looking at any kind of pole impact, which is like a small speed impact analysis, what we did with nonlinear transient. That is what actually you're seeing. So it gives you a good view where you can actually start looking at these models side by side, pre and post. Great way of looking at it. Now, in terms of hyperview details, now I can have all these single model, multi-attribute functionality, what Warren showed. I have all these analysis put together. Actually, I can see it one by one here together. Now you can see some of these great features. You can see the mesh, what you have, the indentation is hitting, the refined mesh and the fine mesh. Those are different sets. They come in and go. And then you have the sag loading and stuff. So the loading and unloading also gives us an option to look at the post, how the deformations are happening in different cases when the load is applied and removed automatically. That gives us an option that gives us see how the unloading happens. Same for any kind of load dent analysis and palm analysis. You can see the setups here done. Now, one interesting thing which I want to show you, which Warren brought up, was in terms of the post-processing diagnostic skills. Now, we have an out file with OptiStruct. When you run, you generate an out file which gives you all these good information about how the model is converged and all the details about the contacts and stuff. And you also have your results file, which is a HTTP file. Now, what can I do is it's a marriage here. It gives you an information of marriage between the out file versus the HTTP file. It gives you more information where you want to go and plot these results and look at what are these things happening in the diagnostics. Like, for example, I have a max penetration, max force, and so on. All these links, what you see, they are listed out here in terms of the node detail and element detail and the contact detail. Gives you enough information for you to go and diagnose any of the problems which you are working on the nonlinear side. So that's there from the OptiStruct HyperMesh side. So let me go back to my slide deck, and then we'll review something on the SimLab side similarly. So moving from the HyperMesh, SimLab, a physics-based environment. So it's a complete different way of looking at pre-processing tool, a great way of looking at how you want to solve your physics. It's a powertrain model we are picking. You have a steady-state thermal analysis. It's AccuSolve based. You can take advantage of running an AccuSolve if you have complex thermal problems and some flow analysis there. And then we do pretension. Then there is thermal stress analysis coming, followed by the pretension, and then those thermal stresses are coming from the CFD tool, automatically mapped beautifully in SimLab, and the combustion pressure analysis, followed by the continuation of all these analyses in the order. So some of the key features which we are looking here is pretension bolts, nonlinear materials, gasket materials, contacts, and stuff. So let's look at the SimLab process in terms of what SimLab methods do. Workflow-wise, SimLab gives you a very, very neat and clean environment where the steps are followed to define a similar way, like the way we do in HyperMesh, because that's a general way of defining a finite element. But it gives you one set of plates to define material properties, and then it gives you a wide range of setups to do pretension, gasket, and contact, and then one solution browser to deal with all kind of physics in one environment, no matter what kind of solver, Altair solvers you're trying to use in that, and post-processing in the same window. Everything in one single window. Let's go back to SimLab now. So let me minimize my screen here and bring up the SimLab here. So this is SimLab for guys who have seen it, not seen it. A SimLab environment, more icons and less tabs and stuff. So in the SimLab environment, you can see I have the fluid and the structure model. While I cut through this section, you can see the red part is the fluid mesh, nicely meshed in terms of the boundary elements and stuff. And these are the contact definitions between the structural components, and then the rest of the engine block and the head are defined here inside. And you also now let's look at the CFD, the pretension bolts at the same time as we are looking at the model here. So now once I click these guys and I can turn off I can hide these guys, and I can just only turn in my head bolts. And you can see also, let me turn off quickly the contacts, because you're seeing a lot of contacts here. Now, when I go into the pre-tension mode, I can actually click on this guy, and I can also see the pre-tension definitions in the model, where you can see at one shot, I can highlight these guys so that you can see the transparency there. So now you can see the definitions of pre-tension in this particular model and how they are defined in SimLab environment. SimLab has a great way of doing bolt modeling, so you can go and create 3D solid bolts, and then you can say these are the sections. This is the bolt based on the height and the head and the length. It calculates and it puts the pre-tension at the right space by defining contacts. Beautiful. Now, looking at this whole model again, I can actually look at the whole model where we want to look at some contact definitions. Now, in this particular model, let me turn off the CFD, the fluid model, and show you the contact definition. So now, if I just click on selecting these parts, and again, let me pick the body, and then click on these parts, and then right-click, and I want to look at any kind of contact manager definition. In SimLab, the environment gives you a contact definition review pretty neatly. So you can actually go, you can do a quick auto contact definition in SimLab, and then probably you can review all these contacts one by one, as you were seeing in the other pre-processing HyperMesh also. So that is one way it gives you an environment where you can define contacts pretty nicely. In terms of contact definitions in SimLab, again, it is the same setup. You go to analysis, contacts, and you can say auto contact creation, and then pick all the bodies, and then say, I want to create contacts between all of you guys. Kindly create it and show it to me, and then you can review and edit in that contact browser panel what we just saw. Now, going to the material part section. Now, we have a gasket material here. You can define in SimLab, doesn't talk about any card definitions. So OptiStruct pretty much neatly explains to you what is the parameters in terms of materials it needs. You also have a beautiful library to grab in some of the materials. And in this gasket material, you can define these tables, gasket loading, unloading. So that's what we've actually defined in this particular model, what you see. Now, that brings up in terms of material definitions, pre-tension definitions, looking at the contact definitions, and the CFD and the structure model. Now let's look at the solution browser of SimLab. In the solution browser of SimLab, pretty much gives you an environment where you can pick the solver based on the physics. So as I said, here you want to pick a particular solver of AccuSolve or OptiStruct, and you want to do what kind of analysis you want to determine to do it. So here what I have for you is thermal analysis, which is done in the CFD side. It defines the bodies of the fluid, and then you define your initial velocities, inlet outlets, and the temperatures. Now, if I jump from this solution set to showing you the CFD results, here's a quick shot. In the same environment of SimLab, a CFD model loaded with the CFD results, you can review them, you can play, animate, and you can get all these temperatures and pressures in one shot. Now, going back to the same browser, I say, okay, I've solved the CFD model. Now I want to do any kind of structure analysis. Now, in the structure side, again, I pick an OptiStruct and I say nonlinear analysis. This is what I'm trying to do, the mechanical analysis here. The first thing is pre-tension. Now, while solving these pre-tension analysis, I can just define these solution parameters in OptiStruct, which pretty much tells me what is needed from the OptiStruct side in terms of the cards for pre-tension loading, pre-tension output, any kind of stabilization and stuff. This is set on a global level, and even at a subcase level, you have these definitions defined in the SimLab environment. So this is at the subcase level, and that's at the total analysis for all the structure analysis together. Now, once I have these pre-tension stuff running, I can go and look at my pre-tension board analysis with the animation and results. So here is a snapshot of what you're seeing, where you have these pre-tension balls and you're trying to look at the displacements and stresses and so on. This is magnified at 150% just to show some animation here. So that's why you see a large scale of order of animation there for the display. Now, coming back to after the pre-tension, now I want to grab those thermal solution which is done by the CFD, and then I want to do that. So that is what is mapped here. Now, if you look at defining any kind of thermal loading or a pressure loading coming from any kind of CFD, what SimLab does is beautifully, it says, okay, what do you want to include? I want to include temperatures from the thermal. The thermal is nothing but the CFD solutions, what I've named it here. and then it'll say, okay, what else you want to map in? I want to map the pressures too. Okay, you map the pressures. So that is what we've been mapping from the thermal loading, and then did thermal and pressure analysis, what you see here. So in the SimLab and in the SimLab side, once you do the thermal and the pressure loading analysis, here is what I wanted to show you, the gasket pressure. Once you have the temperature applied, and then you have the thermal loading coming for the nonlinear static analysis, you have these gasket results, which you can actually see the closed status getting closed, what is the kind of pressure you're getting on these gaskets, and so on, one by one. On the solution browser itself in SimLab, you have a great option where you can actually look at this structure and actually you can say, I want to do export of these settings. So which will give you a great way of saving your process or workflow. I want to do solution. I want to save this as a template. It gives you all this information about the CFD, the pretension, the thermal, and the pressure loading in one shot. And you can save them and reuse them on a different set of an engine or a different set of model, which has a similar setting. You want to reuse it. So SimLab gives you a great automation practice at any time. You can do it yourself. And I can export this model and I can run it. So in the environment, you are not seeing OptiStruct. It's all doing a good job in the backside, and in the front end, you're seeing these results. So that brings up to end of my demo of SimLab. And I think these are two environments which you can take advantage to solve the greatest nonlinear problems. What